Alright, so in this video I'm gonna be explaining another important article with the title infoGCL, Information Aware Graph Contrastive Learning. This NURIPS paper in 2021 is very important. Various graph contrastive learning models have been proposed to improve the performance of learning tasks in graph datasets in recent years. While effective and prevalent, these models are usually carefully customized. In particular, although all recent researches create two contrastive views, they differ greatly in view augmentations, architectures, and objectives. It remains an open question how to build your graph contrastive learning model from scratch for particular graph learning tasks and datasets. So in this work, we aim to fill this gap by studying how graph information is transformed and transferred during the contrastive learning process, and proposing an information-aware graph contrastive learning framework called infoGCL. The key point of this framework is to follow the information bottleneck principle to reduce the mutual information between contrastive parts while keeping task-relevant information intact, both the levels of the individual module and the entire framework, so that the information loss during graph representation learning can be minimized. So this is the graph contrastive learning approach, which consists of 3 stages. For the first stage, we have a graph that undergoes view augmentation. Here we do augmentation. So our augmentations are Q sub I and Q sub J, to obtain two semantically similar views, V sub I and V sub J. Then for the second module, we have view encoding. The two views are fed into view encoder networks to extract latent representations Z sub I and Z sub J. The feature consistency between representations is maximized to optimize the objective function based on contrastive mode, where C sub I and C sub J are aggregation operations applied to representations. So given an input graph contrastive learning aims to learn the representation of graph or nodes through maximizing feature consistency between two augmented views of the input graph via contrastive loss. We decouple a typical graph contrastive learning model into 3 sequential modules: view augmentation, view encoding, and representation contrasting. So given the latent representation, a contrastive loss is optimized to score positive pairs higher compared to other negative pairs. Typically, the negative pairs, I have a playlist for contrastive learning, so I explained that info and CE is just one of the ways that we can do contrastive learning. And theoretically, minimizing info and CE equivalently maximizes the lower bound of mutual information between views of positive pairs. So the lower bound, we have this for mutual information. And the goal of view augmentation is to create realistically rational data via the transformation approaches that do not affect semantic label. Compared to augmentation in other domains, graph view augmentations need to consider the structural information of graph data, such as nodes, the edges, and the subgraph. There are various graph view augmentation methods proposed recently. We follow a similar definition to categorize 4 kinds of view augmentation approaches for graph data. You either can do node dropping, you can do edge perturbation, you can do attribute masking, and this one is also important, subgraph sampling. which samples a subgraph from the input graph. So the augmented views generated in the graph contrastive framework are typically used in a separate downstream task. To characterize what views are optimal for a downstream task, we define the optimality of views. So the main motivation is the optimal augmented views should contain the most task-relevant information, and the information shared between views should only be task-relevant. So for a downstream task T, the goal is to predict a semantic label Y. The optimal views V sub I, V sub j generated from the input graph are the solutions to the following optimization. So we minimize the mutual information between the two views, V sub I, V sub j, while we have two constraints. First, the mutual information between V sub I and Y should be equal to mutual information between V sub j and Y. Also, mutual information between V sub I, one view, and the label should be equal to the mutual information of the input graph and Y. View encoding aims to extract latent representations of nodes or graphs via feeding the data of two views into a view encoder network, such that the generated representations preserve both structure and attribute information. So in representation contrastive, the contrastive modes are unique to graph data because of the structural information inside the graph. Specifically, we consider 5 contrastive modes. In global mode, the graph representations from two views are contrasted. Thus, C sub I, C sub j are averaging aggregation operations in this mode. The local global mode, we contrast the node representations from one view with the graph representation from other view. Thus, C sub I, C sub j are identical transformation and averaging aggregation operation, respectively. The local mode, the node representations from two views are contrasted. In multi-scale mode, we contrast graph representation of one view with the intermediate representation from the other. In hybrid mode, both global, and local global are applied. So here they talk about negative samples, because in contrastive learning, it is very critical. That's why the new generation of contrastive learning try to even avoid completely the negative samples. So these are the data sets that they do for graph classification, like NCI1 mu tag. And for node classification, they use these simple datasets: Cora, CiteSeer, and PubMed. PubMed is harder than CiteSeer. CiteSeer is harder than Cora. Even if you look at the node, you understand something. So we focus on both node and graph classification. They also compared their work with kernel approaches. Look at the graph classification for mu tag. They have 91%, but the kernel approach is almost the same. It means that kernel approach are as strong as these methods. Also for, let's see, for NCI1, 80%, almost the same. but here variance is smaller. So in general, we can say that there is a slight improvement, very slight improvement with state of the art.